Hello, I'm Jeff Boyd from elementarywave.com. This video is about the mathematics of hope despite the rising tide of illness that's keeping us socially isolated. The video says nothing about that epidemic, rather it's about the mathematics of hope. It's based on the most accurate and productive science that humans have ever had, namely Richard Feynman's QED, quantum electrodynamics. This interpretation of QED is known to no one but me, but I'm happy to share it with you. This rising tide of illness is like an atomic bomb that destroyed life as we knew it. How does it help to say that every time a particle strikes an object, it's because the object invited it? Am I saying that we invited or wanted this rising tide of illness? No. If you try to find an answer to the question, why did this happen to us, you will not find an answer. None of the wise people in the past, either religious like Job nor non-religious, ever found a satisfying answer to the question, why did this happen to us? It is not even the right question. The question that should be asked is, given that this disaster happened, how do we live now? Now that is an important question. One way to find an answer is to listen to those like Aristotle who helped our ancestors. Aristotle said that the purpose of life is eudaimonia, which means living and being well. It means being virtuous, loving and being loved. It means having good friends. Aristotle said we cannot learn without pain. Eudaimonia, happiness, is the goal of life. The wise person bears the accidents of life with dignity and grace, like a skillful general who marshals the limited forces. He said, even in adversity, nobility shines through when a person endures repeated and severe misfortune with patience, not owing to insensibility, but from generosity and greatness of soul. A human is a goal-seeking animal. Life only has meaning if the person is reaching out and striving for goals. And of course, he said, teenagers these days are out of control. They eat like pigs, they're disrespectful of adults, they interrupt and contradict their parents, and they terrorize their teachers. I will in this video present an imaginative and distracting new way of looking at nature, something that celebrates the little things that we can still enjoy. If nothing else in this video, my goal is to distract you and take you out of your misery. I propose, believe it or not, to make an interpretation of Feynman's QED, according to which every time an object is struck by a particle, it's because the object said, hey, look, come on over here. Here I am. Come to my house. You bring your good humor, and I'll provide such food and drink as I can afford. We will celebrate life. We're going to make one tiny change in Feynman's QED, namely that we're going to say that the paths of which it speaks are going in the opposite direction as what he thought. This turns out mathematically to be a tiny change. It does not affect the accuracy of the mathematics, but it turns out this is also a helpful change for QED. QED is healthier, stronger after we make this change because it fixes a known problem that Feynman did not know how to fix. In this video, I will demonstrate that anytime any particle strikes any object, it's because the object has invited it, which means that the world we live in is far more interconnected than science has ever told you before. When I speak of mathematics, many viewers wonder if they're going to suffer from nausea and vomiting. But rest assured, there are no mathematical equations in this video. In order to spare you that, I have taken the technical material, the mathematical equations, and put them into a scholarly article published in a peer-reviewed physics journal, which you can get anytime you want, free of charge. And because it's located there, you don't have to be inflicted with it here. Okay, I will explain our theory called TEW, then Feynman's theory called QED, and then how to put the two of them together. Our theory starts with non-relativistic quantum mechanics, which is based primarily on the Schrödinger wave packet. Here you see a Schrödinger wave packet, which is a wiggly line moving to the right. But the question is, in what direction is the line itself moving? You might assume the line is stationary, but in our theory, the line itself is moving rapidly to the left at light speed. Think of it being like a river that's flowing rapidly to the left, while up on the surface of the river, a packet of waves is moving to the right. So we're saying that the Schrödinger wave packet must be seen within the context of it being part of a larger elementary wave moving in the opposite direction. It's well known in quantum mechanics that waves can go in two directions at the same time. For example, a plane wave coming in from the right hits an infinite barrier, bounces off, and travels back to the left. So that's a wave going in both directions simultaneously, as is the case of our plane wave with a Schrödinger wave that's part of it going in the opposite direction, but without the infinite barrier. Now, in our theory, the elementary wave conveys zero energy. Many people would roll their eyes and say, that's impossible. There are no zero energy waves. But that is a naive way of thinking. The Schrödinger wave packet itself is a zero energy wave. It does not carry energy. It carries probability amplitudes for energy. But the wave itself does not push or pull particles. It does no work. It is a zero energy wave. We are just expanding the definition of the Schrödinger wave packet to include its context, which is an elementary wave, which is a plane wave moving in the opposite direction. Here you can see a particle gun or laser on the left, and on the right a detector. From the detector comes a zero energy elementary wave, which is what I'm calling an invitation. That is the detector saying, come, hit me. Come over here. Here I am. Come and get me. So that's going this way, and it's like a javelin. That's what it means to be a plane wave. But inside the javelin there is a button, a trigger. And if you tickle that trigger, out springs a full-blown Schrödinger wave packet going in the opposite direction. Now, under what conditions does something tickle that trigger and make this thing pop out? Well, it happens infrequently. It happens when the javelin, when the plane wave bumps into a particle inside the gun or particle source. The particle tickles the trigger and boom, here comes a Schrödinger wave packet going in this direction. It's all part of the same thing, the javelin and the Schrödinger wave packet. So the reason I say that the elementary wave is like a javelin is that we're talking about one dimension here. The other dimension is amplitude. So the elementary wave goes in this direction preceding the particle. The particle goes in this direction carried by the Schrödinger wave packet. Now I'm going to give you a quick synopsis of the first of the quantum field theories, namely Feynman's QED, which is perhaps the most admired, the most respected science that humans have ever bumped into. This is a double slit experiment in which a photon goes from A to B through a barrier in the middle in which we have drilled 2 holes. The amplitude of it arriving at the detector B is the amplitude of it having gone through the top hole, plus the middle hole. Let's drill a 3rd hole. Now the amplitude of it arriving here is the amplitude of it going through all 3 holes added together. Let's drill 2 more holes, and then keep drilling holes until we have obliterated the entire middle barrier. Now the photon can go on any one of the different pathways. Feynman's approach is called the pathway integral approach, in which you add up all these pathways. When you and I think about a photon going from A to B, we usually think of it going in a straight line, but Feynman's interested in the possibility of it going in all these crooked lines. The photons are always the same color. We have used a rainbow of colors so that we can think about it clearly. None of these pathways, by the way, convey any energy. They're like zero energy paths. They're like paths in the woods. If you walk on a path in the woods, the path contributes no energy to your walk. It just helps you determine which way you might want to go. Now this is what an amplitude looks like. It's a vector in 2-dimensional imaginary space. And for the lowest pathway, which is blue, we're going to put this up here. For the second from bottom pathway, we're going to add another vector, and when you add vectors you put them end to end like this, and then as we add more and more pathways at the bottom, we add more and more vectors at the top. When we get into the middle of the stack, the pathways are more lavender and pink, and so also are the vectors. And now the vectors are beginning to come out of the spiral and come down this way here into a large curlicue object, and then as we get to the top of the stack, where the pathways are red, the vectors begin to curl around this way over here. Now we want to draw a large arrow from the very beginning to the very end, and the length of that arrow is the total amplitude of the photon going from A to B by any pathway. So it is the length of the arrow that is so important. There are a couple of things to be said about this length. The first is that the crooked pathways at the top and the bottom of the stack don't really contribute to the length of the arrow, because their vectors are busy wasting time going around in circles up here. The pathways that contribute to the length most are the more or less straight pathways in the middle of this stack. Another thing to be said about the length of this arrow is that it is very, very accurate when we test it against experiments. For example, if you were to measure the distance from Los Angeles to Manhattan with this degree of accuracy, it would be accurate within the breadth of a human hair. So how can Feynman's method be so precise? Well, here's the odd thing. It can only be so precise if the photon takes every pathway from A to B, which makes no sense. It's a known flaw in his theory, which we will fix in a minute. Obviously, the photon only takes one pathway from A to B. It doesn't take every pathway, and yet the precision of the length of this arrow implies that it must. Another thing to notice is that in Feynman's system, the pathways go from A to B. But logically, there's no reason that that has to be true. The pathways could go from the detector B over to A, and the photon follow it backwards, and you would get the same math except for a minus sign, and that is exactly what TEW says. Now we're going to combine TEW and QED. With TEW, as you recall, every detector, such as point B over here, puts out zero energy elementary waves that go out and over here to point A. Now there can be many of them. They can take many different pathways, as Feynman has made us aware. At point A, the particle which is about to be fired looks out and says, "Whoa, here comes a whole mess of different arrows pointing at me. I've got to choose one of them." So the particle flips a coin and makes that decision at random. I will select that one. It takes one specific incoming elementary wave, and that decision triggers the trigger point, tickles the trigger point on the side of the incoming elementary wave, so that a Schrodinger wave packet opens like an umbrella from inside the incoming elementary wave, and that umbrella carries the particle backwards along the course of the elementary wave back to point B, from which the elementary wave is coming, which point B is a detector. All the other elementary waves that went over to point A, to the gun, are duds. They do not produce Schrodinger wave packets. So the mathematical implications of our system are obvious, which is that we have accounted for the extreme accuracy of Feynman's QED. As I said before, it is the most accurate science of all time. If you measured from Los Angeles to Manhattan, it would be within the breadth of a hair. Because the way we've accounted for that data accuracy is because every pathway is used by the elementary waves. But on the other hand, a particle only goes on one pathway, obviously, and we've accounted for that with this Schrodinger, there being only one Schrodinger wave packet going back. Thus, we have made a rearrangement of QED by combining it with TEW, and our new science is stronger, more sensible than Feynman's QED, which is already the most accurate and the most productive science of all time. So TEW fixes a known problem with QED that no one else knew how to fix. Is that the primary advantage of TEW? No. If you look at that scholarly article that I wrote and mentioned earlier, you'll find in there that TEW banishes all kinds of quantum weirdness. Schrodinger's cat is gone. Quantum experiments change their meaning when you view them with TEW. Experiments that used to say that two entangled particles at a great distance can instantaneously communicate no longer say that. TEW can explain the Bell test experiments and says that Einstein's view of those experiments was wrong. Even things that people thought they knew for sure about the quantum world are no longer true with TEW. For example, there's no wave-particle duality. How can that be? Well, think of it this way. The Feynman experiment we've been talking about for the last 10 minutes is a double slit, triple slit, quadruple slit kind of experiment. And in it you can see that there's no wave-particle duality because the waves go in one direction and the particles go in the other direction, and waves and particles cannot be identical if they're going in opposite directions. This is Jeff Boyd from elementarywave.com. Thank you for your attention to this mathematics of hope, and let's hope that we all develop antibodies to this virus quickly.